wanted to work through an example or an illustration of Fourier transform of discrete data. So this data is on power consumption over the period of a year. It's data that exhibits a number of features in the Fourier transform. We'll see several fundamental frequencies of the power consumption data in the Fourier transform. We'll see higher harmonics of the fundamental frequencies in the Fourier transform. And we'll also see what's called sidebands in the Fourier transform of the data. So it's quite a nice example that illustrates quite a lot of features that you will meet in Fourier transforms. So the data that we're going to examine, the data that we're going to explore, is power consumption data. And it's power consumption data over an entire year that was recorded in 15-minute intervals. So there are about 100 15-minute intervals in one day. There are about 36,500 intervals in 1 year. And the data that I have is contained in a file. That file is just a single column of data of these roughly 36,000 entries for power consumption on 15-minute intervals. So we're going to read in that data and then basically make a discrete Fourier transform of that data. And then we're going to examine the Fourier transform of the data. So let me start by just saying a few words about the code. Here's my code. I'm going to perform the Fourier transform with the SciP Fourier transform package. Specifically, I'm going to use two functions, FFT, which performs the Fourier transform itself, computes the Fourier transform of one-dimensional discrete data. And then secondly, FFT frequency, or FFT FREQ, which allows us to transform the array index on the Fourier transform data to a frequency scale for the Fourier transform data. So that's going to be handy. Rather than have the data just indexed by a indices, say K, we're going to have the data indexed by a frequency of cycles per day. So I'll import these two library functions. And then in the second cell here, I'm going to use the numpy package. It's load text. It allows me to read in data from a text file. And as I say, I'm just reading in data that is a single column of data with 36,000 entries. And I'm going to fill an array, a numpy array. I just called it megawatt, MW, for the to contain this data, to store this data. There's a few things I do before I actually perform the Fourier transform on the data. Firstly, I need to know the number of entries exactly in the data. So I get that from the length of the array. I want to define the time interval between successive data points in the data. As I say, it was recorded at 15-minute intervals. I'm going to think of my data and the frequency of my data in cycles per day. And so the length of time between successive measurements or between successive data points is 1 day divided by 24 hours in a day, divided by 4, the number of 15-minute intervals in 1 hour. And so that's the time interval dt in units of days. I also want to make an array of all of the times throughout the year in units of days. So I've created an array here with the NumPy function linspace, starting from 0, running to the end of the year in units of days, and having the 36,000 roughly data points correspond to all the data points that are read in. So that's n, dt, and t. And then I've just got these two lines here calling the two SciP functions to perform the Fourier transform and to define the frequencies of the Fourier transform components. So firstly, here's my call to the function FFT that performs the Fourier transform on the time domain data, that's MW, to create the frequency domain data, that's FMW. And there's one little point here that, as I mentioned in class, the data in the frequency domain contains the data and a mirror of the data. So the bottom half of the frequency array is the frequency distribution of the data. The upper half of the frequency array is a mirror of that frequency distribution. And so I've sliced the array that is returned from calling the function FFT. I've chopped off the top half and just cut the bottom half. So I just got one copy of the frequency distribution. I then call this additional function FFT frequency. This is the function that allows me to plot the data, the frequency distribution, rather than plot it versus just the index of the array, to plot it versus frequency in some units that are sensible for us. I'm going to plot it in units of cycles per day. That means it'll be easy to spot distinctive features in those units. One other line here. I decided I would not only just plot the frequency distribution of the power consumption data, but I would plot the data, the period distribution of the power consumption data. So the period is just the inverse of the frequency. The period in seconds is the inverse of the frequency in hertz, or in this case, it will be the period in days will be the inverse of the frequency in inverse days, cycles per day. And so I make that additional calculation of a second array that is an array of periods rather than an array of frequencies. And then I've just got some calls to plotting functions to make 3 plots. One plot is the original data in red. So this is the power consumption in 15-minute intervals versus time for the roughly 36,000 data points. The middle plot in blue is the frequency distribution. And so this is what we're going to be examining in detail. And then the lower plot in green, that's the corresponding period distribution. And so that's my code. And I'm going to go to a few slides where I've annotated the plots to pick out some of the features that are important in these plots. Okay, so here are my slides. You just see the 3 plots again. Top one is the time domain distribution, and then the lower 2 are the frequency domain distribution and the corresponding period distribution. I'm going to take these plots and I'm going to expand the scale on the next couple of slides, and I'm going to annotate certain features on the next couple of slides. But before I do that, let me just make a comment about the range of the frequencies that are observable in the power consumption data. So you look at the plot of the frequency distribution, it runs from zero cycles per day, to close to 50 cycles per day, 48 cycles per day. So that's the range of frequencies that we can observe. And that's determined by what we call the Nyquist limit. So the Nyquist limit says that you can't see an oscillation. You can't see a signal in your data that has a period shorter than 2 samples, 2 data points. In our case, we sample every 15 minutes. 2 data points are 30 minutes. So we can't see a period in the data that would be shorter than 30 minutes, shorter than about 1/50th of a day. So that's the minimum period, the shortest period we can see. The maximum frequency, the largest frequency we can see, is then about 50 cycles per day. And so the upper frequency on the frequency plot is the Nyquist limit, based on the rate at which we sampled the power consumption data. Okay, so on this plot, I've changed the scale for the frequency distribution. I've changed it from that full range that went to almost 50 cycles per day to a range that goes to just above 2 cycles per day. So a much smaller range. And by expanding the scale, I'm able to see a number of important components. So let me start mentioning them. This peak here at 1, this says that there's a frequency in the data that has a period of one day. So it's a frequency that is 1 cycle per day. And, that's not surprising. Power consumption probably varies during the day. While we're sleeping, maybe we use less power. While we're awake, we use more power. So to see a frequency in the power consumption data with a period of 1 day corresponding to a frequency of 1 cycle per day is not surprising. And that's a fundamental frequency in the data. There's a second clear fundamental frequency in the data, and that's down here. It's at the frequency is 0.14 cycles per day. It's this large peak here, and 0.14 cycles per day corresponds to 1 cycle a week. So this is a period of 1 week. It's not surprising to see that in the data also. Sounds sensible that we might use a different amount of power at the weekend when we're not at work compared to when we're in the weekdays and at work. So we might expect to see a period of a week in our data, and indeed we see it. We see a cycle correspond to 1 cycle per week. So that's this peak here. In addition to the fundamental frequency of 1 cycle a day and the fundamental frequency of 1 cycle per week, there are harmonics of those frequencies. If the daily dependence was a simple sine wave variation of the power consumption, then we just see the fundamental frequency. If the weekly dependence was a simple sine wave, then we just see a single frequency. But the daily dependence and the weekly dependence are periodic, but they're not likely to be sine waves or cosine waves or sinusoidal. So if they're just periodic but not sine or cosine waves, we expect to see higher harmonics that reflect the true nature of the periodicity. And so we see that for both the fundamental frequency of one cycle a day and the fundamental cycle of one cycle per week. So here's the fundamental frequency for one cycle per day. And here's the lowest harmonic. This is a frequency that is twice that fundamental frequency. So this corresponds to two complete cycles a day. And that's clearly in the data. Likewise, over here on the left, this is this large peak here. This is the fundamental frequency of one cycle per week. And then you see at 0.28, the lowest harmonic of that, which is a frequency that corresponds to two cycles per week. And so this is the lowest harmonic of the weekly cycle. And so those features are in the data. There's one other feature in the data. I'm not sure I fully understand this feature. It makes sense that power consumption varies during the day. So we have a daily cycle. It makes sense that power consumption varies during the week. So we have a weekly cycle. But there's also a peak at 0.033. It's this peak here, which corresponds to a 30-day period, corresponds to 0.033 cycles per day, which is one cycle per month. And so that too is in the data. And I really don't have a good explanation. I'd be interested in a good explanation of why that's in the data. I wanted to show you a couple of other features that are in the data, frequency data, and mention a couple of other frequencies in the data. So in addition to the cycle of one cycle per day and its harmonics, and the cycle of one cycle per week and its harmonics, there's some other peaks. And I've indicated them here. So in the neighborhood of the one cycle per day, that's the fundamental frequency here at 1. To the left, there's two peaks. And also, if we were to expand the scale, to the right, there's two smaller peaks. Likewise, if I go over to this higher harmonic, which is 2 cycles per day, to the left of it, there are also 2 peaks. And to the right of it, there are 2 peaks. Now, those satellite peaks to the left and right of the one cycle today, and to the left and the right of 2 cycles today, are called sidebands. They're actually located at 0.14 and 0.28 cycles per day to the left and right of the fundamental frequency, and 0.14 and 0.28 cycles per day to the left and right of the higher harmonic. And they correspond to satellites in frequency at a frequency of one cycle per week, or 0.14 or 0.28 cycles per day. And so these are sidebands. So sidebands appear in the frequency spectrum when you have 2 or more frequencies in your data. And we have 2 or more frequencies in our data. So as a simple example, let's just suppose we have a frequency F1 and a frequency F2 that were different. If our underlying time domain distribution was simply a sine wave with a frequency f1 plus another sine wave with a frequency f2, then our frequency domain distribution would just contain two peaks, two frequency peaks, one at f1 and the other one at f2. So we just see the two fundamental frequencies. But suppose instead of the data, the time domain data, just being the sum of one sine wave with frequency f1 and the other sine wave with frequency f2, there was a component that involved the product of the two sine waves. So it'd be the sine of a frequency f1 times the sine of a frequency f2. That's like an interference, an interaction between the two different frequencies. And that generates the sidebands. And so these sidebands are a reflection of an interference between the weekly and daily cycles. So you might imagine there's a periodic cycle of one day, there's a periodic cycle of 1 week. And in the time domain data, there's some component that is a product of those two cycles, the 1 day, 1 week cycles. And so that's how you get the sidebands. And so that's what we're seeing in our data. One last comment about the data. I've expanded the scale on this frequency plot. So now it runs, rather than from 0 to roughly 2 cycles per day, it's going from 0 to 10 cycles per day. I've also changed the scale so that it's a log scale, so I can see a greater range in the data. And I pointed out that there are many higher harmonics of the daily cycle. So here on the left is the fundamental frequency, 1 cycle per day. Here's the lowest harmonic of that. This is 2 cycles per day. We've already met that. But you see 3 cycles per day, 4 cycles per day, 5 cycles per day, 6, 7, 8, 9 cycles per day. They're all in the data. That's indicating that the periodicity, the daily periodicity of the data is quite different from a simple sine wave, a simple cosine wave. It is periodic, but it is a very different periodic structure that's made up of many frequency components. So that's one point. The other point is that surrounding sort of satellites to the harmonics, you'll see the sidebands. So we see sidebands for the fundamental frequency, these 2 peaks here, for example. We see sidebands for the lowest harmonic, these 2 peaks on the left, these 2 peaks on the right, and so on and so forth. So here's the next harmonic. We see 2 peaks on the left, 2 peaks on the right, separated by a period that is 1 week away from the harmonic itself, and so on and so forth. So the 4 cycles per day harmonic has satellites, sidebands. The 5 cycles per day has satellites, sidebands. So that's another interesting feature in the data. Anyway, the purpose of this was to explore some fairly complicated data, the power consumption data, which has a number of frequencies in the data, which you would never see in the time domain. You'd never make all this detail out in the time domain. But by decomposing it or transforming it to the frequency domain, you see this sort of wealth of features from the fundamental frequencies, cycles per day, cycles per week, to the harmonics of those frequencies, to the sidebands involving the interference between the daily and the weekly cycles, to other things that maybe we don't fully understand. The monthly cycle, for example, I don't fully understand that.